All right, so just a lot of exposure to different nomenclature here. You have to memorize all the ones I highlighted in blue, and you know, I don't know, a while back ago, those ones. Or you just look at the chart in the handout. Well, it depends on how your approach to nomenclature is. Basically, you have to memorize all of them. However, if you know like certain patterns and stuff, you might not have to memorize all of them. Like when I took nomenclature, I had just memorized all of them. I just made it. I had a thick stack of flashcards and just memorized everything. That didn't work so well, the flashcards. So then I switched to writing it down. But it was just rote memorization. If you know some of the patterns, then you might save yourself. So, for example, the acid names. If you know the anion, you can figure out the acid name, or just memorize the acid. You have two choices how you do it. Mm-hmm. Mm-hmm. Right. If you do that, then you don't have to memorize them individually. Otherwise, you might just memorize them. Like, I think I memorized them individually, the acids, which is kind of a waste. But different people will prefer that. Some people don't like the ich aus thing, or ich aus hydro ich. Some people prefer that. But if you know the pattern, then you can name acids that aren't on your list of memorization. So you might get thrown an acid, but you might know the anion name, and then be able to figure it out. Then chapter 7 is the chemical formula relationships we talked about. Then chapter 8 is the chemical reactions. Now the chemical reactions, I'm focusing on not all the reactions here. Like these combination decomposition reactions, single replacement. I'm focusing on the double replacement reaction for right now. So your test is going to focus on these double replacement reactions. Or we call them metathesis because when you look at the net ionic form of these, let's see, I forgot to post this. When you look at the net ionic form, it doesn't have the AB plus CD pattern. And so rather than calling them double replacement, looking for a double replacement pattern, you just look for ions, an ion combination pattern. Let's see, I think I lost that. So we could take a look at one that we looked at yesterday, which was the
chapters of the test that were 6, 7, 8, and 9.
Mm-hmm.
We're not doing chapter 5.
5, 2, yeah. 5, 6, 7, 8, 9. On the sample test, I had through 10, I think.
It's 5 for 9 this time?
5 for 9?
Yeah. When we look at a reaction like this, does that look like a double replacement to you? No, but it is. It's a double replacement reaction. And so I don't call them double replacement. That's why I call them metathesis reactions instead of double replacement, because there are multiple patterns for the exact same reaction that we'll see. And you don't want to get too hung up looking for this. So this is metathesis or double replacement. How about this one? Let's see. What does that look like to you? Does that look like double replacement to you? AB plus CD? Yeah, like triple replacement. It's the same thing. This is the same metathesis. These are all metathesis reactions. So you're just looking for the best ion combination. And so if you have a whole bunch of ions, which ions are going to form the best ion combination? And so I just said metathesis are favorable ion combinations. So it doesn't matter how many. You know, if I threw in a third reactant here, we call these reagents. If I threw in a third reagent, a lot of people would be stopped cold. That is, they wouldn't know how to proceed because it doesn't fit the AB plus CD pattern. And then some people would be able to figure it out, like triple replacement or whatever.
How would you determine the best ion combination?
You know, you just look at all the ions that you have and then figure out what the best combination is. And so you just start swapping the ions and then look. But how do you know? How do you know? You look for what are favorable ion combinations from yesterday or the last week or something. I don't know. One. You look for ion combinations that form precipitates. What ion combinations form precipitates? Insoluble ones, the solids, right? The insoluble ones are going to have strong attractions between the ions so that it forms a strong lattice. What types of things? Well, what types of things form strong lattices? One, you could just do very general. You know, high charged ions will form strong lattice. Or two, the best thing maybe is just to memorize the solubility rules. Some people struggle with this. It's not easy. And so rather than memorizing them, you start to look for patterns, but the patterns are more complex because there are some +1 cations that are insoluble, like silver. And then there are lots of +1 cations that are soluble, like group 1 and ammonium. And so there are some tricks to it. But if you kind of see the pattern, then you can kind of figure it out. But some of the things are difficult to figure out.
So just make, so then 2 would be gas formation and 3 would be...
Yes, right. You remember. That's good. 2 would be gas formation. Unfortunately, requires some memorization, but less than the solubility rules.
That would be like we did yesterday.
Right. And then 3 would be not strong. I'm careful not to say strong because it doesn't have to be a strong acid. You know, there are 7 common strong acids. It just has to be a stronger acid to weaker acid. For the stronger acid to weaker acid, you're going to be given a table.
Oh, weaker acid and stronger acid.
Weaker acid to stronger acid is going uphill.
Oh, stronger.
Yeah, stronger. It's got to be stronger to weaker. That's that downhill direction because stronger acids are more reactive, Weaker acids are less reactive. Uh-huh.
Is the table we're being given in the textbook?
The table that's going to be given is the one in the supplement. That's the table that's going to be given.
Just, again, because number 3 is already given to you, you just figure out when you get the table.
Yeah.
And number 2 just memorize.
Yeah, number 1 and number 2 you have to figure out. But normally the precipitates are quite common, like lead 2 chloride is common, or lead 2 iodide is common precipitate. Yeah, those are common.
Follow-up question, the gas formation,
Mhm.
can you list some common gas formations that occur? We had one yesterday. Is there the other ones?
Yeah, the most common one is this. If you're going to learn one, learn this one. What happens to H2CO3? It becomes water and carbon dioxide. So if you have limited memory capacity, this is the one you need to know 100%. You'll need to know this one. The other ones aren't as important. So for example, the other ones were HCN. What else?
H2S.
Yeah, what else? First thing is, do you even have these in your notes? You know,
H2SO3.
H2SO3. H2SO3 does what? H2O and SO2. H2SO3 isn't as common. We don't work with sulfites as much because sulfites aren't so stable. Sulfites are reactive. So if you have sulfites in air, they don't live so long because they get converted. Sulfites get converted into sulfates. That's it. These are antioxidants kind of thing. This one's more common. Yeah, ammonium hydroxide is a bit more common. So carbonic acid and ammonium hydroxide are the two big ones.
We had a couple of these problems the other day, right?
Yes.
So I'm about to have one day.
Carbonic acid. Ammonium hydroxide, yeah, we did. So.
Will you break ammonium hydroxide into 2 and or no?
Yeah, ammonium hydroxide is unstable. It breaks up into, yep, good. NH3 plus H2O. So this is from yesterday or day before, I don't remember. That. How do you remember this stuff? Yeah, and like, you know, memorization is not so easy. But to make it easier is give yourself time. And thing is, like chapter 6, you want to do that early so that you can review it. The more times you see it, the easier it is to remember. And so the more times you see it, if you only see it once the night before the test, it's very difficult to memorize. I don't have that kind of memory. And some people can look at it and remember, but I don't. I have to see it repeatedly over and over again. Otherwise, I'll completely forget it.
What does the first one say? HC. No,
The-
the bottom one? The first one?
HCN.
Oh.
HCN is aqueous or gas. And so it depends. Some of it will stay dissolved, some of it will come off as a gas. H2S is the same thing. H2S very little dissolves. This is borderline. This is just SS, slightly soluble. This is, or gas. It's primarily gas in this case. Both of these are primarily gas. CO2 for sure is a gas only. Very little CO2 dissolves in water. SO2 is going to be a gas. Ammonia is going to be aqueous or gas. Ammonia is quite soluble. And so H2S, this is minimal solubility. And HCN has minimal solubility too, but a little bit will dissolve. Ammonia has quite a bit of solubility. Ammonia and water mix quite well, and so you might not be getting that much gas here. But if you have like a ammonia cleaner, like Windex here, you can smell the ammonia coming off a little bit. So there's a little bit of gas coming off.
For the SO2 and the CO2, they don't have any charges, do they?
No charge. Those are neutral. All these are neutral. So I was focusing on the double replacement reactions. And so you want to get good at the double replacement reactions for sure. Get good at the nomenclature. What we're going to do is I'm going to go back and let's take a look at some other types of reactions that we'll encounter. Oh shoot, I think I didn't see it. Some other types of reactions that we'll encounter are, these are redox reactions here. And I'll talk about these. Maybe. Now. All right.
What chapter is this?
Chapter 8. This is element plus element redox reaction. And so, like, for example, we could have carbon as one element and oxygen as another element. And so if we try to burn carbon and oxygen, what will we form? CO2. We could potentially form carbon monoxide or and CO2, depending on the conditions. The conditions will dictate this. So if we don't have enough oxygen, we might form carbon monoxide. What we do in our prediction is multiple products might form. So we're going to try to make life easier, and we'll just go to the max. That is, we'll do complete reaction. So what we're going to do is we're just going to assume complete reaction. And so we know that carbon will go all the way to carbon dioxide. The carbon is a solid, oxygen is a gas, and CO2 is a gas. And so this happens to be balanced now. If I had carbon monoxide, I'd have to use 1/2 an O2, 1/2 of a mole of O2. I can't use 1/2 a molecule. If I did carbon monoxide at the particulate level, I'd have to go 2 carbons plus 1 O2 gives 2 COs. Double it, everything. That's a combination. So we're going to just max it out. So here we're going to take aluminum and react it with oxygen. What's the max charge on aluminum?
3.
Yeah. And so what we end up forming is aluminum is going to get,
2,
and then oxygen is going to get,
3.
and then we are going to have to figure out the charge. So this is 3 oxides, 2 aluminums, and we form Al2O3, aluminum oxide solid. And then we'll try to balance this. The way I balance this is like this. I have 2 aluminums here. I'll put 2 aluminums here. And then I have 3 oxygens here. But I have 2 oxygens here. So you know what I do? I do 3 halves. If I do 3 halves, then that gives me 3. 3 halves times 2 is 3, correct? And then I double everything. And so I end up with 4 aluminums plus 3 oxygens yields 2 aluminum oxides. Yeah, on the first equation. The first equation, I have 2 aluminums and 3 oxygens on the left, and I have 2 aluminums and 3 oxygens on the right. That's the first equation. On the second equation, I double everything to get rid of the fraction. I don't want the 3 halves fraction. And so both are acceptable. You can have fractions there as long as you're dealing with mole quantities. You could have 3 halves of a mole or 1.5 moles of oxygen. It's not a problem. But if you don't want any fractions, then just multiply everything by 2. You can get rid of the fraction. Let's do another example here. Okay, copper plus oxygen. We could potentially, what are the charges on copper? No, 1 and 2. 1 and 2 based on its position in the periodic table.
We choose 2.
We would choose 2, right, because that would be the, yeah, and so we'd go to CuO. But, note that we could have formed what's copper 1 oxide, the formula for copper 1 oxide? Cu2O. We could have formed this if we didn't. But, to keep things simple, we'll just go to the end. So if you have a brand new penny, it's shiny, but eventually it reacts with the oxygen and air and starts to discolor. So copper 1 oxide is kind of red-brown. And so initially your pennies will form copper 1 oxide on the surface. And then after a while, they'll turn black. Copper 2 oxide's black. And so really old pennies will look black because we've gotten copper 2 oxide, and then it stops. And so the ultimate end would be that.
So, like, on the test, if there's a question like this where an element has
Multiple charges, right.
will you accept, like, either answer?
No, I just go to the end one. Technically, either answer would be correct, but to keep life simpler, we'll just go to the max. And it's like when iron reacts with oxygen, we have a choice. We could find iron 2 oxide or iron 3 oxide. Right? Iron 2 oxide, what's the formula for iron 2 oxide? FeO. What's the formula for iron 3 oxide? Fe2O3. We're just going to go to Fe2O3, rust. Ultimately, it'll end there. And so what we're going to do is we're just going to bypass the iron 2 oxide and just go straight to the rust. That's just to, so we'll just go to the max charge. If you're given a choice, you know. Aluminum, we're not given a choice because there's only one charge for aluminum. Let me make a more difficult example here. What if we burn phosphorus in oxygen? What do you expect to form?
Phosphate?
It's not going to form phosphate because of the charge. If we form phosphate here, which would be reasonable, what's the cation? We can't have anions alone without cations because we need to maintain charge neutrality. Otherwise, the voltage gets way too high. What we call it potential. So it's not phosphate. It's going to be an oxide of phosphorus. What's the max charge on phosphorus? Yeah. So the max charge on phosphorus is 5. What's the charge on oxygen? 5 plus is a very difficult charge to maintain, but that's what we use to predict these things. So we're going to end up with a formula of P2O5. P2O5 is actually the empirical formula. The molecular formula for it is P4O10. Tetraphosphorus dicoxide is what we actually form when we burn phosphorus. But P2O5 is what you'd predict. You wouldn't know P4O10 unless you had some additional information. P2O5 is actually a solid. It's not a gas. And so what do you name P2O5? What's the name of that?
Diphosphate?
That's correct. You guys hear that? Diphosphorus pentoxide. And so let's balance this equation. This is the way I balance this equation. I'll just save the oxygen for last. So we have how many phosphorus? 2 phosphorus over here on the product. We need 2 phosphorus here. That gives us 5 oxygens here. How do I get 5 oxygens here? 5 halves.
And then double everything.
Yeah, and then double everything to get rid of the fraction if you want. So this would be 4 phosphorus solids plus 5 O2s yields 2 P2O5. O2 is a gas. P2O5 you wouldn't necessarily know, but that's a solid. That'd be it. These are examples of redox reactions. In redox reactions, what we have is we have electron transfer.
What's the final product?
P2O5. P2O5 solid is the final product.
But the balance would have to be 4 phosphorus and 5 oxygen.
Yeah. 4 phosphorus, 5 oxygens, and then 2 P2O5 solids, P2O5. That would be the final balanced equation.
It's 2 because we doubled it before, right?
Yeah. It's 2 because we're doubling everything. And it was really 1, but we doubled everything. So 2 doubled is 4, 5 halves doubled is 5, 1 doubled is 2. So that's how we got it.
Oh, but how do we know when it's like solid aqueous? Because I gotta understand. It's solid gas and liquid. Should we be given it that way, like the products?
No, sometimes it's difficult. All ionic compounds are solids, basically. All salts are solids. In the or aqueous if they're soluble and there's water present. But in pure form, the salts are solids. All metals are solids except for mercury, right? Now, non-metal oxides, a lot of those are gases. like carbon monoxide and carbon dioxide are gases. Well, when the molecules get kind of big, then they turn into solids. And so something like P2O5 is kind of a big molecule, so it could be a liquid or a gas. You wouldn't necessarily know, but how you know is, this is how you know. Do you want to figure it out theoretically using quantum mechanics? No. It would be way too much work. And so what we know is we just have a few reference points. You know, a few reference points to help you. And those few reference points are memorized. And so what we do is, okay, how long is the drive to San Diego? And you say, oh, the drive to San Diego is short. But what is your reference point, you know? For somebody, yeah, it's short. If they have to drive cross country, it would be a short drive, right? But to you, maybe it's a long drive. And so what we need is we need some kinds of key reference points. So what you do is you memorize. Well, I don't want to know if it's short or if it's long. I'd like to know how long it takes. Maybe it's 2 hours without traffic. Okay, that's that. But how did you come up with that number? Well, that number you came up with is because you memorized it, or you from experience you've memorized it. You know, or somebody might have told you. I don't know. But we need certain reference points. How long is the drive to San Francisco? Oh, it's going to be a long drive because it's far away, but you know, you'll want some kind of reference points memorized. And so people get tired of, oh, it's a long drive. They want to know a number. How long is the drive to San Francisco? You know. And so how do you know that? Well, you know, did you calculate that? Did you sit down with a map and calculate it using the speeds and this, all that? And figure out how many stops in this. No, so there are some reference points you have memorized, and so some of the reference points you'd have memorized is you start memorizing little bits of information here so that you can make predictions. Usually what we try to do is we try to memorize the extremes. You know, the extreme on one end, the extreme on the other end, and then everything else will be in between. And so the extreme would be, what would the longest drive, you know, take, and what would the shortest drive take from here to San Diego? It's like, you know, it's good to know the extremes. That way you have an idea. Because like the drive from here to Big Bear, how long does that take? Does anybody know?
To Big Bear?
Yeah, to Big Bear. 2 hours, 2 hours plus, right? But you know, one time I was trying to get home from Big Bear, and it took 6 hours from Big Bear to.
It took me like 5.5 hours with traffic one time going there.
Yeah, that's crazy. So you would know some of the extremes there. Unfortunately, those are memorized too, and people who don't, you know, have anything memorized, like, okay, how long's the drive to Big Bear? Oh, it's kind of far. It's going to take you a long time. That's not very useful. And so in science, people want some more concrete, you know, stuff. And so that's why, you know, even though a lot of people say, oh, you don't need to memorize anything, there are certain things that are very useful to memorize. Once I was stuck on the 101 freeway because the tanker truck, I was like the second car behind, and the tanker truck was blocking the entire freeway because it was leaking out acid. It was leaking out acid. There were giant plumes of brown smoke coming out, and then the news crew was right in front. So I was just watching them tape the news, and the reporter was saying, oh, this is a massive hydrochloric acid spill on the freeway. And I was thinking, that's not hydrochloric acid, because those are brown plumes, you know. Brown plumes like that are associated with nitric acid, not hydrochloric acid. So automatically I thought that's wrong. Of course they could have maybe Googled it, but they had no idea that hydrochloric acid doesn't give brown plumes like that.
You set them straight.
I didn't set them. They were in the middle of their news broadcast, so I didn't set them straight. I said, excuse me. Maybe I should have, because
That's not right.
I mean, this was like when I was taking the equivalent of Chem 4, I think, something like that, or Chem 1A. All right, we have the reverse of these.
Reverse of redox is decomposition.
No, this is a decomposition redox. And so, for example, CO2 can be decomposed into the elements. So if we take CO2, if we decompose into the elements, these are decomposition into elements. So what we do is we go from a compound back to the elements. And so the compound CO2 would decompose into what elements? Yeah. And O2. They're neutral. Yeah. So this would be an example of a decomposition. What would carbon monoxide decompose into? C plus O. 1/2 O2 or just O? Yeah. It would have to be 1/2 O2. If you don't want the fraction there, then what would you do? Double it. So we'd end up with 2 carbon monoxides would decompose into 2 carbon solids plus an O2 gas. So it's just the reverse. This is the reverse of the combination reaction, the redox combination.
Can you go back one? Thank you.
Water decomposition, this one's being studied a lot because water would be a good source of hydrogen. Except in order to do this decomposition, it's not so easy. The reverse is very easy. This one's difficult. And so typically we use a chemical separation technique. Do you know what the chemical separation technique that we use to separate hydrogen from oxygen and water? We don't burn it. The reverse it would work. We burn hydrogen with oxygen to get water. And so burning is the reverse. This
So
is
we unburn it?
yeah. How do you unburn it? And so going reverse is what we call combustion. This one is more difficult to do. We typically use electrolysis. It's a very common reaction. And so you can electrolyze water to form this. In fact, this is how, this is how they separated. This is way back in the middle of the 20th century. In the middle of 1900, they used electrolysis to separate heavy and light because one reacts slower, the other reacts faster. Like the lighter water molecules react faster in electrolysis, and the heavier ones react slower. And so by doing that over and over again, eventually they got pure heavy hydrogen, which they can use to make water.
The product will be, after using electrolysis, we would get 2 hydrogen and half an oxygen.
Yes, right,
And then you would double it again, you get 2 H2.
right, exactly.
So whenever we're doing oxygen and you're left with a single one, remember to do it 1/2 because
Right, 1/2 or some fraction of it works quite well. And so this is the decomposition of water into its elements. And this is a redox reaction. There's electron transfer.
is it decomposition?
I'm sorry?
Is it decomposition?
Yeah, decomposition. Decomposes. So it's a decomposition reaction. Okay. Here's some more decomposition reactions here. Um, this is just showing a reversible change. In the forward direction here, this is decomposition.
Redox.
Yeah. And the reverse direction here is showing combination redox.
Redox has to do with oxygen, correct?
Redox doesn't, historically, yes, that's correct. Because oxygen is very abundant, and it's a great oxidizing agent, what we call oxidizer. And so historically, but you know there are even more powerful oxidizers than oxygen. Like what would be more powerful than oxygen? Things like chlorine, fluorine are more powerful than oxygen. Fluorine wants the electrons more. Those would be more powerful. Permanganate is more powerful. Permanganate's an excellent oxidizer. Actually, I could just look them up right there. Dichromate. Do you see oxygen on the right side at minus 1.23? Do you see minus 1.23?
Yes.
That's oxygen. And the ones below that are stronger. So it goes dichromate, chlorine, permanganate, hydrogen peroxide, and fluorine. Those are stronger. The ones above oxygen there are weaker. And so historically, redox was with oxygen, but now we can use a multitude of oxidizers, some weaker, some stronger. And so these reactions aren't always going to have oxygen. Let's do another one. What is the most powerful oxidizer? The most powerful oxidizer is not oxygen. On the chart, the most powerful oxidizer is fluorine. So tell me what we'll make if we burn. You can burn carbon in fluorine gas, just like you can burn carbon in oxygen gas. So we can burn this in fluorine gas. What would we form?
Carbon and fluorine.
Yes.
Would be CF2.
CF2, CF3,
CF2.
CF2, CF3.
CF2 because it's in carbon. I don't know if I think carbon.
What's the max on carbon? Max positive charge.
4 to negative 4, so it's CF4.
CF4. This fluorine is a -1, so we'll need 4 fluorines to balance out that. And so it's CF4. Carbon tetrafluoride is what we call CF4.
Because they're non-metals.
Yeah, carbon tetrafluoride is, can you burn carbon tetrafluoride? No, you can't. You can't burn carbon tetrafluoride. In fact, it doesn't burn carbon tetrafluoride. And so we call carbon tetrafluoride a class of chemical called fluorocarbons. Fluorocarbons used to be used in refrigerants, like refrigerators, that kind of stuff. Also, they're looking at using these as synthetic blood because they're so unreactive, these fluorocarbons, as a fluid. Carbon tetrafluoride, what would you expect? Gas, liquid? I would guess a gas. But potentially it could be a liquid. For example, carbon tetrachloride is a liquid. It's a CCl. Do you remember what CCl stands for? Yeah, good. Wow, that's good. Let's balance this. This one will be a lot easier to balance. What number? 2? Okay. Yeah, and so this is a combustion reaction or redox reaction, but it doesn't involve oxygen at all. It involves something even more powerful than oxygen. Yeah, and so what we call the fluorine is we call this an oxidizer, like we would call oxygen. Oxygen is an oxidizer. This is also an oxidizer. Historically, oxidizer refers to oxygen, but now oxidizer refers to anything. anything that takes electrons. What happens is originally these start off at 0. These are neutral, 0 and 0. And then fluorine tries to take the electrons from carbon, and the max it could take is 4. However, this is not ionic. The weird thing is this is a molecular compound. So molecular compounds do not consist of ions. And so this is not really an ionic. This is just for bookkeeping here.
So no charges.
And so carbon in the +4 is not very stable. So what we often do is we write carbon Roman numeral 4 to indicate that it's not a monatomic ion. And so these are not monatomic ions. This is a molecular compound in which the carbon appears to be in the +4 state. And so we use a Roman numeral there instead. So it is not made up of ions.
And after you give the example of copper, for example, would that be ionic?
Yes.
Because it's a metal, correct?
Right. So the copper 1 oxide and the copper 2 oxide that we formed is ionic.
And you wouldn't have charge, would you have the charge?
They would have the charges, right?
So now I guess back to the beginning, molecular no charge and then ionic will have the charges.
Yeah, a molecular doesn't consist of ions, but what we do is we do the same kind of analysis so that we can figure out the correct formula. The correct formula is going to be this. It's going to behave as if it were kind of ionic, and then it's going to max out. So would you expect to find CF5? No. Could CF2 exist? Yes. CF2 could exist, but it depends on how much fluorine we have. If we have plenty of fluorine, we should be able to make CF4. So CF3 could also exist. But what we don't want to do is we don't want to have a whole bunch of different ones. We just want to go to the end, the max.
Let's say we said like Fe, iron oxide.
Right. That's why we went to iron 3 oxide and didn't stop at iron 2 oxide, because we were just going to take it to the end. Now, for the variable charge, the end is not the max. It would just be the higher of the two variable charges. This is redox, correct. This is redox because electrons, let's talk about oxidizers, and carbon is a reducer. A reducer is what we call a fuel. And so if you have a fuel and you want to use the fuel, you need an oxidizer. So if you had a gallon of gasoline won't do you any good unless you have, not carbon dioxide. Carbon dioxide doesn't work for burning gasoline. What do you need in order to burn gasoline? If you have a gallon of gasoline, you have to mix, we have to mix the fuel with ethanol is a fuel. Methane is a fuel. We have to mix methane with what in order to get it to burn? Oxygen in air. We have to mix it with air. Cars do this. Cars used to have things called carburetors, which were like your barrel on the burner. And the carburetors would mix the fuel with the air. That's the job of the carburetor. Now they have, these air things, and they have injection. So they inject the fuel and mix it with the air. And so what we need is an oxidizer. So if we have a fuel, we need an oxidizer in order to use the fuel. So if there's no air, there's no combustion.
They take out the thing in the car.
The carburetor?
Yeah.
Oh. Probably in the 1980s, they took out the carburetor.
Wonder. We have-
The carburetor is still being used. Yeah, in motorcycles. Some motorcycles still use carburetors.
We have a truck and it sells a carburetor.
Oh, okay. Still has a carburetor. What year is the truck?
1979.
Okay, 1979. Yeah,
It's nice.
yeah, yeah. That's a classic
But it's a
thing.
carburetor. I was like, I've seen different. I've seen the carburetor.
Yeah, yeah. So the carburetor is going to mix the fuel, which is the reducer, with the oxidizer, which is the air. Uh huh.
I might have missed it. How do you know that it's molecular or ionic?
Because it's a compound of nonmetals. Compounds of nonmetals, except the ones that contain ammonium, are like, for example, ammonium chloride is ionic because we recognize the ammonium ion and the chloride ion. But anything else is molecular.
Ammonia and ammonia derivatives, right?
Yeah, right. You got it. So this is molecular. Molecular is not going to consist of these ions like this, but we do the ions like this to keep track of what forms, what's reasonable.
So it's because they're non-metals?
Yes, nonmetals, exactly.
The ionic is
Yes.
and then the molecular is just the molecular formula units.
Molecular form molecules. The something like carbon tetrafluoride, you know Teflon? Teflon is made up of carbon and fluorine atoms, but they form long chains, which we call polymers. So they're a bunch of carbon-carbon links. This would be the simplest one, and these chemicals are very unreactive chemically. The carbon-fluorine bond is very strong and hard to break, so they don't really react. And the carbon's already maxed out. It's completely what we call completely oxidized by the oxidizer fluorine. And so this is called complete oxidation here, complete combustion of the carbon to form this. This, however, is potentially gas, and what happens is the gas rises up into the atmosphere, and even though it's unreactive, there are reactions that weren't anticipated. You know, carbon tetrafluorides were promoted as these wonder chemicals because these wonder chemicals were so inert, they're so stable. But unfortunately, what the early scientists didn't foresee, and this happens all the time, they didn't foresee these things because nature, the world is kind of complicated, right? And it's not so easy to come up with some kind of simple model that mimics nature. And so as these rose up, then they were hit by UV, ultraviolet light, and it broke these bonds. So ultraviolet can break these bonds. And then what we call create are free radicals, and these free radicals set up a chain of reactions which end up destroying the ozone layer. So it used to be back in the 1970s or something like this, you didn't have to wear so much sunscreen. You'd go outside and you'd get terribly sunburnt at the beach. But now you have to wear a lot of sunscreen because the ozone layer is a lot thinner than it was back in the day. But you know, these are unforeseen things. You know, a good theory should be able to predict these unforeseen things, but good theories are, you know, are hard because the math is too difficult. If the math becomes too difficult, or the theories aren't complete, they don't see all the factors that go into these things, and so there are some theoretical predictions about the weather, about lots of things, theoretical predictions about drugs and drug actions. You know, I was just listening to, I don't know if you ever listen to, there's a YouTube channel, Science Without the Gobbledygook. Have you heard of that one? Sabine, yeah. She had this thing where she was talking about why is the world left-handed? And it turns out a lot of the molecules that we have are what we call left-handed molecules. And then she was talking about this one drug. You know, it's hard just to make the left hand. If you're making gloves, you'd make both the left-hand glove and the right-hand glove. And you'd have a pair. Well, that's kind of how the factory works. The factory, at the chemical factory, it produces both forms, the left hand and the right hand. And like if you buy, did I already talk about this? Like if you buy a bottle of ibuprofen, you know, how many tons of ibuprofen do they make per year? A lot. Like a lot. But did you know half of that's wasted? It's half of that is the wrong form. You know, we have left-hand form and right-hand form of ibuprofen, and we can only use one. But fortunately, that was only wasted. Is that? I'm sorry. It's like a cockroach. Sorry. Cockroach. I didn't know we had roaches. But anyway, it turned out that one of these things for pregnancy, did you hear one of these old drugs for pregnancy relied on the left-hand form, but it also contained the right-hand form. The right-hand form caused a whole bunch of birth defects. And then it was never approved in the U.S., but it was approved in Europe. So a whole bunch of kids were born with birth defects, unfortunately. And then they finally pulled the drug. But, you know, the theory is difficult. There are lots of cases where the theoretical predictions were way off. Because the systems are so hard to model, you know. I mean, they're predicting that this year was going to be a low snow, like the La Nina, but it turned out that the snowpack is really pretty good. So anyway, we're going back to this. We have the oxidizers. Oxidizers take electrons. Reducers give electrons. And so oxidizers are what we call electron poor. Fluorine would like to become fluoride. And reducers are electron rich. So something like carbon tetrafluoride, is carbon tetrafluoride a good fuel? No, this would be a very poor fuel. It would be a very, very poor fuel because carbon is in the +4. It has no more electrons to give. And then fluorine's in the -1. Yes, fluorine's in the -1, but fluorine doesn't want to let go of that. It wants to be -1 and it stays there to make fluoride. So fluoride's fairly stable. People use fluoride in their toothpaste. They used to fluoridate water to promote healthy teeth. And so they put maybe, I think it was like a half a ppm in drinking water. And then this is based on certain like European villages had, you know, did I talk about this already? Their population had excellent teeth, you know, and then they tried to trace why, like excellent being not much tooth decay and that kind of stuff. And so they tried to narrow it down. Why did this village, the villagers in this village have such great teeth? And they found out that, there was fluoride in the water. And so they were talking about putting fluoride in the water here, and they did put fluoride in the water here. But then people are claiming, unintended consequences like this whole ozone thing and everything else. It's hard to predict, right? The same thing with the drugs. It's very hard to predict because how many biochemical reactions are happening in your body? You know, is it easy to come up with some kind of concrete absolute? You know, so scientists veer away from talking in terms of absolute, but some scientists have been talking in terms of absolute, and it's building mistrust, I think, you know, between science. Science should be truthful in how far their predictions can go. Did you have a question?
I was going to ask if there were any side effects.
Side effects of what? Of what?
Of the fluoride.
Of the fluoride? Well, some people are claiming there are side effects. Other people are claiming there are no side effects. You can read. The thing that's good about the fluoride is it's a good, healthy debate. You know, a good, healthy debate, people on both sides can present their views. What's been happening lately is one side of the debate has been completely silenced, whereas the other side has not. And it turned out the silent side turned out to be correct after all. But anyway, so the best thing is to just do your own research and then come up with your own conclusion, you know. because the information's out there on both sides for fluoride. I still use fluoride toothpaste.
Are we not supposed to? We're not supposed to.
I don't ingest it, right? And I still, when I just went to the dentist, they gave me a fluoride rinse, and I had to not eat or drink anything for 30 minutes afterwards. So. But some people will probably decline, for sure. They'll decline because of what they've read, you know. And so you look at what observations were there that caused them to decline the fluoride rinse, you know. And so you look at that and then see, you know, that's the evidence in support or to refute it.
Have you read any of that like scare you or?
Yeah, I've read some stuff about causing developmental delays and also brain issues as well. You know, but it depends on the studies too. You know, a lot of these studies have like multi-factors that will impact, you know, the observations that you see. So how do you know it's due to fluoride and not due to something else? And so those types of things have to be sorted out. But the whole fluoride debate, you know, originally when I thought about the drinking water, I thought that was a good idea, but it's no longer in drinking water. I think there are too many people who are opposed to it, you know. Originally, but I hadn't looked at all the data. You know, you should look at the data and make up your own mind. You know, it's your choice. That's the good thing. It's your choice. You know, you can go out and buy other water without fluoride. But if it's forced, you know, if somebody's going to force you to do it, then force you to drink fluoride or force you to take fluoride, that's a different story. You know. And so that's what the whole debate, recent debates were about. Okay, single replacement reactions are another type of redox reaction. And single replacement reactions are going to have an element in a compound. And so the way we recognize this is A is an element and BX is a compound. And so the reactions are going to have this pattern. A plus BX yields AX plus B. And so this would be an example of single replacement. Copper is our A, and silver, what's this called? Silver nitrate is our BX. And this is going to form AX plus B. So we have copper plus silver nitrate is going to give us copper, all right, copper with nitrate. When we take copper with nitrate, we have a choice.
Copper 2.
Yeah, it could be copper 1 or copper 2. Which one should we do? Should we do both of them? It can kind of get messy if we do both of them.
Copper 1.
We should do copper 1?
You just see how we just do the max?
We do the max. Let's just go to the max. It'll be easier. And so what we're going to do is we're going to do copper 2. So if we do copper 2, what's the charge on nitrate? -1. So how many nitrates do we need? 2. And so we need 2 nitrates for every copper, and that's what we have here, 2 nitrates for every copper. So they went to copper 2 nitrate, not copper 1 nitrate. We want to just go to the max.
Now we balance it.
And then B is just silver, but over here it's silver ion. Over here it's going to be silver metal. And so it's going to form a compound plus an element. And so a lot of people make the mistake, it's silver ion over here. What's the charge on silver ion? Oh, well, +1. It's a fixed charge, +1. We don't put a plus here because what happens is the silver ends up gaining an electron.
And that throws it out.
And so it changes. Redox are electron transfer, so the charges change. the charges change. Now, combination decomposition, we look for forming more stable products. So combination decomposition, there's not a simple thing. Let me go back to this for a moment. Which one do you think is more stable? Water or hydrogen and oxygen mixed?
Water.
Water is more stable. And so which way is downhill? In the top reaction, the downhill direction is to H2O. This is the bottom, that's the top of the hill, right? In the bottom reaction, which way is downhill?
Left to right.
Yeah, left to right. We call left to right forward. The forward reaction is favored here. In the reverse direction, in the top reaction, the reverse direction is favored. And so we try to figure it out. Here, carbon with fluorine, which one do you think is downhill? Do you think carbon tetrafluoride is more stable or carbon with fluorine gas?
Carbon to fluorine gas.
The gas to elements.
Okay, so you're thinking this way, the reverse is downhill. So you're saying this is more stable?
Oh,
No, this is more stable.
Isn't it generally that the products are more stable because they're like
It's a
it's
compound.
balanced and then
Yeah, but sometimes it's hard to say. I could give you some other kind of ridiculous reactions, but yeah, this is favored. So a lot of these, it's the direction of oxidation. This is favored. Like for example, copper. Copper is fairly stable, but eventually, what happens to the copper? It'll start to discolor. And what happens to iron? Iron will start to rust. Copper will start to discolor. However, does gold, what about gold? Gold doesn't oxidize. And so how do we know these kinds of things? So if I did gold, let's do this side since I ran out of room. If I did gold and oxygen, what would you predict? Now gold is a bit trickier because gold forms plus 1 and plus 3, and we said we're just going to take it all the way
max.
to the max. So we'll go to gold 3. What would gold 3 oxide be? Oh, good. Can you do these in your head, or do you need to write them out?
You get my next in a while.
Okay. Au2O3. Au2O3 does not exist. In fact, the downhill direction is the reverse. Gold doesn't oxidize. And so gold is stable, but all the other metals do. And so, not all. We have what are called the Nobel metals. Have you ever heard of those? The Nobel metals, yeah. Or the coinage metals. These metals are very difficult to oxidize. And that's with any oxidizer, oxygen. Even if I use fluorine here, fluorine is the most powerful oxidizer. So if I'm going to oxidize something, I could try using fluorine. But even with fluorine, gold is difficult. Maybe with fluorine, gold might. But the Nobel metals are difficult to oxidize because they're unreactive. They don't want to lose their electrons. So in order for gold solid to go to gold 3, we'd have to lose 3 electrons on each gold. So Nobel metals are unreactive. The Nobel metals are gold, Au. What else? Platinum, Pt. Palladium. Osmium, iridium. Osmium, iridium are very rare, etc. Silver is borderline. Silver is starting to become reactive, more reactive, and so it doesn't last as long. Silver tarnishes. Copper is really at the cusp. Copper, maybe copper at the very end. No. Copper would be at the end of the unreactive metals. It's reactive a little bit, but it'll stay lustrous for a while. Like a copper penny will stay shiny for a while. Like if you have a new roll of copper pennies, it'll stay shiny for a while. To copper. Or if you think of jewelry, which jewelry will last the longest, probably, in terms of luster? Copper? No, gold. These are hard to oxidize. But most other things aren't so hard to oxidize. So if we have copper, we'd expect it to oxidize.
Yeah, this one is one of the examples of a trick question.
No, I don't think I'd make a trick question regarding this.
Going back to the single replacement one, the balance would be 2 silver nitrate, right?
So if you ask like what are the Nobel metals, would copper be one of them since it's slightly reactive? Would we want to put that down?
Borderline. Copper would be borderline. If Nobel metals, it'd be clear. Nobel metals, you could debate copper. And so if I asked Nobel metals and I didn't want to have a debate, I'd say you'd just pick gold, something like that. I wouldn't throw copper in there because somebody could argue the opposite. It depends. We did double replacement. Let's take a look at some more single replacement reactions here. Magnesium definitely is not a Nobel metal. Magnesium is a very reactive metal. Magnesium reacts with hydrochloric acid. What's the formula for hydrochloric acid? HCl. Okay, what forms here? MgCl2 plus. Okay, what's the formula for hydrogen? H2. Okay, let's put down the states. HCl should be.
Gas.
It's in the pure form. It's a gas, but hydrochloric acid is always aqueous. Yeah. Magnesium chloride. Chlorides, bromides, and iodides are all soluble except for are all soluble except for silver, lead, and mercury. And hydrogen should be a gas. All right, now let's balance this.
Hydrogen chloride on the left. That's it, right?
Yeah, that's it. Now, the driving force is not the same. As double replacement or metathesis. So, for example, gas formation doesn't work.
Just to make sure, everything that we talked about, except for the world replacement, counts as readouts, right?
Yeah,
Readouts.
so far, right.
So where are they driving force?
This reaction forms a lot of gas. But has no driving force. This is uphill. To have a driving force, we need to go downhill.
So would we say like decomposition is always
No, we can't say that. And so what we have to do is we have to figure out the driving force for redox. So let me talk about the driving force for redox here. These go hand in hand. It's going to be strong, strong to weak, weak, or stronger, stronger to weaker, weaker. It's never going to be strong, weak, weak, strong, or any other combination. If we're going weak to strong, that's not considered driving force, but strong to weak. Strong is more reactive, less stable. So if we have a stronger oxidizer on the left and a weaker oxidizer on the right, that's favorable. Two, there's another way of looking at it. We have the more active element. The more active element is stronger reducer. Elements are reducers. To the less active element. Weaker reducer. So for, this is the driving force also. And so this is or, 1 or 2. Now, we use different tables for this. For this one, we use the redox chart. For this one, we use something called the activity series, which is the upside down redox chart. The activity series is a part of the redox chart, but it's not the complete redox chart. Just looking at a part of it. All right, we'll take a break here, and then we're going to continue after the break. Zoom here. So we talked about double replacement reactions. And one of the most common double replacement reactions are precipitation ones. This is one of solid forms. The other is gas formation, and the other is stronger to weaker acid. So let's look at this reaction here. What is this? Sodium nitrate. Soluble?
yes.
all sodium salts are soluble. Silver nitrate soluble? Yeah, all nitrate salts are soluble. So when I look at this sodium salts, nitrate salts, those are soluble. So both of these are going to get aqueous. This is both a sodium and a nitrate. For sure this is going to be soluble. Sodium salts are soluble, nitrate salts are soluble, so aqueous, if there's water present. If you evaporate all the water, then what's going to happen? You're going to get the solids. But we're not going to evaporate all the water. However, you don't have to evaporate all the water here because silver and chloride form a favorable ion combination. And we call that a solid, which is called a precipitate. So this is just precipitation of silver chloride.
Or driving force would be silver chloride.
Yeah, driving force would be precipitation of silver chloride. All we need is one driving force.
Can you explain the structure of the CE to IE to NIE again? Because that structure is just a little bit confusing.
This is the CE, and then the IE, we look. Sodium chloride, is it a soluble salt? Yes, so what does it split up into?
Sodium and chloride.
Okay, what's the charge on sodium?
Plus.
What's the charge on chloride? Yeah. And so this one we just split up. So we could just do that here if you want. This one is already balanced. Otherwise we'd balance it first.
In the CE.
Yeah, we balance it in the CE. But since it's already balanced, we don't have to balance it. Saves us a little bit of time. Now, what I do is I leave off aqueous just to save time because that's a lot of writing to have to write aqueous over and over again. And so, yeah, everything else you're going to do. So you said this is going to break up into Na plus Cl minus. Does this one break up? Yeah, soluble salts break up. And so this is going to break up into, not iron, silver. What's the charge on silver?
Plus.
And the charge on, what's NO3 called? Nitrate. Okay. Is this a soluble salt? Yes. And so this is going to break up into Na plus NO3 minus. Is this a soluble salt? No. And so just leave it alone. Okay, this would be the IE, the ionic equation. This is the CE. What's the NIE?
So we just do the iron, silver plus iron.
Yeah. Silver plus chloride. This is going to make silver chloride. So this is the favorable ion combination here. Silver ions like chloride ions. The sodium ions are spectators, nothing happens. The nitrate ions are spectators, nothing happens to
If they're
those.
soluble, they break up.
Yeah.
And,
Right.
and in the second line, or the second, I guess, past the arrow of the product, if they're insoluble, just keep the same.
Yes. And then the final thing we write here is our driving force, which is the precipitation of silver chloride. Does that help? All right.
And the redox ones is just one line.
No, redox we can do the same thing. So for example, the redox, let's take a look at the one we just did. Did we finish that one? Magnesium solid plus 2HCl led to magnesium chloride plus hydrogen gas. Again, I'm going to omit aqueous. This is the CE. And let's go to IE. Magnesium, is that a strong acid? Yes or no? No. Is that a strong base? No. Is that a soluble salt? No. So just don't do anything.
If they're horrible,
We'd break it up into ions. Is HCl a strong acid? Yes, so break it up into ions. What ions would it break up into?
H plus,
So we need to make sure we keep track of the how many. We need 2 H pluses and two chlorides. And we have to make sure the charge is there. A lot of people were neglecting the charge, but it makes a huge difference chemically if it's charged or not charged. Magnesium chloride. Chlorides, bromides, and iodides are all soluble except for silver, lead, and mercury. So that's not one of the exceptions. So magnesium chloride is soluble. It's a soluble salt, so we're going to break it up into what?
Magnesium
A charge
2 plus
and
2 chloride.
okay, do I write 2 chloride like this?
No, 2 in front.
No, a 2 in the front.
Then you put the charge as well, right?
Yeah, and then we'll put the charge. All right, is hydrogen gas a strong acid?
No.
Strong base? Soluble salt? And then just don't do anything. Just leave it alone. All right, this is the IE. And then for the NIE, we see what doesn't react. Magnesium, did it react or not react?
Did it react?
It did react because what happened to magnesium? What happened to magnesium is we went from no charge
So ionized?
to +2. That means it lost 2 electrons. So magnesium's a field. Do you know magnesium burns? Have you ever seen magnesium burn? I'll burn some magnesium in the lab.
Right?
It's a bright white color. In the
Fireworks?
hmm?
These fireworks?
It's used in fireworks. It gives a bright white light in fireworks, so they put magnesium in fireworks. They used to use magnesium in flash bulbs in the 1800s. They had a bulb, and inside the bulb was air and magnesium. And all they had to do was ignite it, and then it gave a bright white light. And so magnesium metal is what we call electron rich. Like most metals are electron rich. But magnesium ion, can you burn magnesium ion? No, magnesium ion doesn't burn.
Just curious, when did they stop using the magnesium lamps or light bulbs, like you said?
Flash bulbs?
Yeah.
Expensive, really expensive. Now they can do it much cheaper.
How do they make the light bulbs like white now instead of yellow?
The light bulb's white light. The hotter you heat it, the brighter it glows white. That's for the tungsten filaments, and so they can control the output of the light by the temperature. And so they have different temperature light bulbs that you can get depending on the color spectrum you want. Or for these are LEDs up here, and the LEDs they have a green LED, a red LED. The red and the green LED have been around for a long time. The red LED has been around since the 1970s, I think. And then the green came in around the 1980s, maybe 1970s, late. But the blue LED didn't come in until much later. And so if you take red, green, and blue, you can make white. And so if you look at an LED TV, there are 3 LEDs in there: green, blue, and a red. And they mix the colors to get different
Is that why
colors.
when the screen goes kind of like wonky, you see all the different dots?
Yeah, if you see the different dots, if you get really close, then you can see 3 colors of light. And when they mix, they make the rainbow of colors. You can get the rainbow of colors from those 3. All right, what are the spectators here? Not magnesium. Magnesium definitely changed.
Chloride?
Chloride and hydrogen definitely changed. Can you burn hydrogen gas? Yes. Can you burn hydrogen ions? No. And so magnesium solid plus 2H plus yields magnesium 2 plus hydrogen gas. So if we dissolve magnesium metal in hydrochloric acid, we're going to effervesce hydrogen gas. Hydrogen gas is a CCG. And so we do the same for single replacement. We do the CE, the IE, and the NIE.
And this was an example of redox.
Yeah. This is an example of redox, so the driving force is totally different. So up here, the driving force was precipitation. Down here, the driving force is not precipitation, not gas formation. Gas formation is not a driving force for redox. And so what we have is something called the activity series. we use for this. Activity series, I think, is in Chapter 9. Let me open Chapter 9. So what we say is there is a driving force for this. This is more active. More active means a stronger reducing agent. A stronger reducing agent means more electron rich. So stronger reducer. And hydrogen turns out to be less active. So this is odd. Hydrogen burns very well. In fact, hydrogen is very explosive. But it's weaker than magnesium, so that goes to show you magnesium is quite powerful. Reducers are fuel, so magnesium turns out to be a better fuel than hydrogen. Problem with magnesium is it's a solid. But then the problem with hydrogen is it's a gas. And so this is it. But oddly enough, magnesium is a stronger or better fuel, more electron rich than hydrogen. More electron rich, it's easier to lose electrons. Hydrogen is very electron rich though. You can easily lose electrons. If we go backwards, this is a competition actually, by the way. When we're comparing the left side with the right side, we're looking at a competition between the left and the right. This is a redox acid base. I'm not redox. This is double replacement. This is this neutralization. These are double replacement neutralization. I don't even want to talk. I don't want to classify these as a separate reaction. These are just double replacement reactions. Let's get rid of that. It's just the driving force is different, and so the driving force is going from a stronger acid to weaker acid. It follows the same pattern. This is AB plus CD yields AD plus BC. So this is double replacement.
B is here switched. Which is C.
BD. I mean, CB, sorry. I got them backwards. CB. So I don't like to subcategorize this as a separate reaction. This is just double replacement. So let's just take a look at this double replacement reaction here. A, what is A? Hydrogen ions. B? Sulfate ions. All right, C? Aluminum 3 plus. And D? Hydroxide. So what we're going to do is we're going to have hydrogen ions with hydroxide. Hydrogen with hydroxide makes what? Water. They wrote water HOH. We can do the same, or we can write H2O. So hydrogen with hydroxide, and then aluminum with sulfate. So what's the correct formula for aluminum and sulfate?
2 aluminum, 3 sulfate.
Yeah, 2 aluminum, 3 sulfate. And the cations are always written first. So we'll get Al2SO4, 3. And so we need a driving force. So the driving force here is going to be stronger acid, H2SO4, to weaker acid, water. And that would be our driving force. And so this is just a double replacement reaction, essentially.
So when it's a neutralization reaction, what is it?
We're going to weaker. We're helping neutralize the acids. Strong acids are very reactive, and so.
Impossible to replace with the several driving forces that
Right, right. And so neutralization just means you're going from a stronger acid to weaker acid. Whenever you're going from stronger to weaker, you're kind of neutralizing the strong acid.
Which is one of the driving forces for.
Yeah, it's just one of the driving forces for one of the driving forces for this. Now let's do some additional analysis of this particular reaction. I'll just write it here. All right, so we had sulfuric acid. What was the formula for sulfuric acid?
Yeah. H2SO4.
H2SO4. Plus, is H2SO4 aqueous? Yeah. Sulfuric acid, all the acids you can treat as aqueous. Aluminum hydroxide. What's the formula for aluminum hydroxide? AlOH3. Good. Is that aqueous?
No, it's solid.
No, it's solid. Hydroxides are all insoluble except for group 1, ammonium and calcium, strontium, barium. This is not one of the exceptions. This is going to form water. What's the formula for water? And aluminum sulfate. All right, so let's balance this. I have 2 hydrogens, but I have 2 hydrogens here, but sulfate, how many sulfates do I have? 1, how many sulfates over here? So I'm going to go 3 here. And then how many aluminums do I have over here? 2, and I'm going to go 2 here. So that's going to make how many waters? Now water I want to balance by ion. So this is what I'm going to do. I'm going to treat water as a hydrogen ion and hydroxide. So how many hydrogen ions total do I have? 3 times 2 is 6. How many hydroxides do I have? 2 times 3 is 6. So I'm going to have 6 waters. Does that make sense? So one advantage of writing it like this is we can treat water as a hydrogen and a hydroxide to help balance. Makes it life easier. All right, now let's go on to aluminum sulfate. Is that aqueous or is that? Sulfates are all soluble except for silver, lead, mercury, calcium. Well, silver, lead, mercury, calcium, strontium, barium. It's not one of the exceptions, so it's aqueous. All right, so this is the CE. Let's go to the IE. Tell me the IE for this. Strong acid? Yes? No? Yes. Strong acids we break up into what? 3H plus? Plus HSO4 minus? Or SO4? 3HSO4 minus. Wow, you got that correct. This one why don't we completely break off the H's? We have 2 H's. Why don't we go 6 H pluses and 1 SO4 2 minus? Yeah, it's stubborn, right. It doesn't break off. That's good way of thinking about it. Is this a soluble or insoluble salt? Insoluble. Only soluble salts we break up. Insoluble salts, we just don't do anything. Just leave it alone. Water, strong acid? No. Strong base? No. Soluble salt? No. Then just leave it alone. Aluminum sulfate, strong acid? No. Strong base? No. Soluble salt? Yes. So we need to break it up. What do we break it up into? 2 aluminum, 3 sulfates. How many charges? I mean, what's the 2 minus? Okay. And then we go to the NIE. In the NIE, what are the spectators? Do we have any? No spectators. So the NIE is the same thing as the IE. Everything is a reactant in this one. Everybody participates in this particular reaction.
Can we check if it was cycle salt, strong base, with strong acid, and it did not qualify? We don't really know.
Right. And the driving force again is stronger acid, H2SO4, to weaker acid, water. This is our driving force here. Water is a pretty weak acid. So to summarize, this is from chapter 8. We had, okay. Got it? Okay. To summarize, we had these combination element plus element decomposition. We had the single replacement. These first three are redox. And the first two are kind of the same. One's one direction, the other's the other direction. Then we had our double replacement. And then we're going to look at I'm sorry? Yeah, we're going to talk about the activity series now in chapter 9. Let me get the PowerPoint. Chapter 9 here. Let me save this chapter 8 PowerPoint. So we already talked about chapter 9, the electrolyte properties here. And we learned about strong acids ionize almost completely, so roughly 100%. Excellent conductor. Major species. Minor species, weak acids partially ionize. And for the acids, we don't have to memorize that. You know, the acids, we just use this chart. So the acid chart is going to be given here. So we'll have this. This is the acid chart. The only thing that's not going to be given are the names of the acids. And so we can figure out if we're going from stronger acid to weaker acid. We just want to go downhill on the left. Now, what about the activity series? And let's take a look at the activity series. Do they have it here for us? So we want to learn about the driving force for single replacement and redox reactions. We haven't talked about that many redox reactions yet. The activity series is not, oh, here it is. Maybe I'll just give you the activity series. This is the activity series here. There's some additional stuff here. Some of these metals are super reactive. So for example, lithium metal. Lithium metal is quite dangerous. Do you know why? Because is it? Yeah, used in batteries. Fires. This is a big fire danger. Lithium is an excellent fuel. You know, a lot of metals are electron rich, so we got to watch out. A lot of these metals can easily catch on fire, in a sense, and they're water reactive. So, for example, sodium metal reacts violently with water. And so these metals will react with water to make hydrogen gas in a single replacement reaction. Whereas these ones will have more difficulty. They don't really react with liquid water, they'll react with steam or acid. And so these are called the active metal. All these metals that react with normal acids are active metals. You don't worry about all the little details here. We'll look at the details in more depth later. It's hard to, this is just straight memorization. If we look at it on the redox chart, there's patterns to it, and the patterns are a lot easier to remember than these little comments that they write here.
Will we be given that, or?
Yeah, you'll be given something like this, probably. Yeah, I'll just give you something. You don't have to memorize it, but what's the least active metal on the chart? Do you see? Gold.
And we're talking about before, gold.
Yeah, take a look at the least active metals. Gold. What's this one? Platinum. Palladium.
Silver. Mercury. Copper.
The antimony. Antimony would be, I guess, in a similar category. Then we have Hydrogen is an excellent fuel. Lead, tin. These are even better. Yeah. And so the most active ones are at the top of the activity series and the least active are at the bottom. And so the reaction that we were looking at was magnesium versus hydrogen. If we look, which one, I told you magnesium's more active, it's a stronger reducer, and hydrogen's less active. So we can see that in the activity series here. Magnesium's higher up in the activity series, hydrogen's. So we're going downhill. What we want to do is we want to go downhill. If we have to go uphill, that's not a driving force. And so the driving force will be downhill. All right, so let's take a look at some single replacement reactions here. These are, again, redox reactions. These are the ones from the previous. This is an example of a single replacement reaction here. I could use different ones. This is what we call the reducer. This is the oxidizer. So there are different things I can use to oxidize the metal. Oxidizing the metal just means we're removing electrons off magnesium. So magnesium is going from 0 here to over here it is +2. And so in this case it's an A plus BX pattern. A plus BX yields, yeah, this is just single replacement. So let's use the activity series to figure out if we have a driving force. Do we have a driving force for this particular reaction? And so the first thing you do is you look at the two elements. The element on the left is, and the element on the right is iron. So which one is, do you think, well, this one you might not even need to look at the activity series. Which one do you think is a more reactive metal, magnesium or iron? Magnesium. And so this is going from a more active to a less active. Iron does burn like steel wool, but it doesn't burn like magnesium. It doesn't get white hot like magnesium does. And we can verify that by going to the activity series. If we go to the activity series, then we'll see magnesium is one of the more active metals. The group 1 are the most active, followed by the group 2. So group 1 metals are by far the most. Then the group 2, and then the transition metals, the metals in the middle, are less active. And so magnesium versus iron, iron's here, magnesium's there. So this is downhill, magnesium to iron's downhill. That's what we want. So let's go ahead and do this one then. As an example, well, maybe we'll just do it like this. The problem they did though is they took this to what iron? Iron 2. They didn't go to iron 3, right? And I told you you should take it to iron, the max. We should take it to the max, iron 3. Now, they did it to iron 2 because it happens in steps. Now, you don't necessarily know this, and so this is why I have another chart. Rather than giving you the activity series, I have a chart that will give you a little bit more information. And so I'll show you the chart here, but we'll probably get more practice with the chart as we go along. Here. Where is my redox chart? I'm going to give you, you see that chart there? This is the chart you're going to get. And from this chart, we're going to tell what ions we're going to form. So we have to be able to read this both forward and backward. And so if I have copper metal here, and I go backwards here, what can copper metal form? Does it form copper plus 2 or copper plus 1? It forms copper plus 2, so we take it there. However, if we look at iron, when we go to iron, iron goes to plus 2 or plus 3? It goes to plus 2. It goes to plus 2 initially, and it stays at plus 2. And eventually, the iron plus 2 gets converted into iron plus 3. And so what we're going to see is we're going to see what happens to these. So iron plus 2 will eventually get converted into iron plus 3. And so what we're going to do is we're going to use this chart to figure out what charges and what species we form. So getting to use this chart takes some time to get familiar with it. And so we'll spend a little time to get familiar with it as we go along here. What do I do with my PowerPoints? And so you would have had some information. I would have put iron 3. I would have went all the way to iron 3 chloride. But for iron, initially it'll go to iron 2. Eventually that's going to turn to iron 3. Iron 2 chloride is not stable. If you had iron 2 chloride in the lab here, it'd last a few hours. When you come back, it's iron 3. It gets oxidized. But initially we'll have the iron 2. It's like the copper. Initially it forms copper 1, the red-brown on your penny, and then eventually it will go black, but it takes time. Rather than having all that mix-up, we'll just go to the ultimate end, except for something like this. For redox, we're going to use the redox chart. The redox chart is just, that way we don't have to think about things. If you want to figure out what it goes to, just look at the redox chart and see how they're connected, and then you'll be fine. All right, anyway, iron, not a strong acid, not a strong base, not a soluble salt, so don't do anything. Hydrochloric acid, strong acid, split it apart. And we got to make sure that we keep everything balanced. Hydrogen, not a strong acid, not a strong base, not a soluble salt, leave it alone. Iron 2 chloride, chlorides, bromides, and iodides are all soluble except for silver, lead, mercury, so it's soluble. So split apart. And then look for the spectators. The spectator here will be chloride. And so what we're doing is the acid is attacking the iron metal. In other words, the acid is oxidizing the iron to iron 2. Oxidize means losing electrons. And so we have something called oil rig. Have you heard of oil rig?
The oil rigs?
Yeah, like oil rigs out in the ocean. Yeah, well that's where this comes from. Oxidation is loss of electrons. Reduction is gain of electrons. And who causes oxidation to occur? The oxidizer. Yeah, if you lost, let's say, it's kind of weird, but the oxidizer is not oxidized. The oxidizer oxidizes something else. The iron is oxidized by the oxidizer, H+. So if somebody stole your electrons, you'd say, my electrons were oxidized. But you wouldn't say you were the culprit. The oxidizer was the culprit who stole your electrons. Well, iron got its electrons stolen by the oxidizer, and in the process, it was oxidized. We'll talk more about it. It takes time for those types of things to click. Here's another single replacement reaction. Let's take a look at this one. This is zinc solid with copper 2 nitrate. And so this is A plus Bx yields AX. So zinc, what's the charge on zinc?
2 or 3.
Only one charge on zinc. No. Only one charge on zinc. What is it? No.
It's 2.
It's 2. Zinc, cadmium, and silver Zinc and cadmium are plus, and silver is always +1. So zinc nitrate is this. We don't call it zinc 2 nitrate, we just call it zinc nitrate, and copper, metal. So what's more reactive, zinc or copper? Zinc. Yeah. It's funny because copper metals are mostly, not copper metal. Copper pennies are not copper. Do you know what copper pennies are? Zinc coated with copper. The zinc is very reactive, so you have to be careful. All right, so there's a driving force. We're going from more active zinc to less active copper. In other words, this is downhill on the activity series. Let's take a look at the activity series here and confirm that it's downhill. Can you see it?
It's kind of hard to beat copper unless you're those.
Yeah. Yeah, right, it is. You have to be one of the Nobel metals to beat copper. Copper is hard to beat. Silver can beat it though. Silver is more stable than copper. All right, then we look for the spectators here. Actually, we ionize the soluble. This is soluble salt ionized. This is soluble salt ionized. The elements we don't ionize, the neutral. And so what we see is nitrate doesn't play a role here. It's the copper 2. The copper 2 is taking electrons. So zinc loses 2 electrons to copper. Copper goes to copper 0. And in the process, zinc loses the 2 electrons to go to Zn2+. So this is what we call electron transfer. There are 2 electrons being transferred from zinc, the reducer, to the oxidizer, copper 2. Copper 2 is an excellent oxidizer. Copper 2, you can oxidize lots of different things with copper 2. So it's not just oxygen that acts as an oxidizer. Zinc can be oxidized by oxygen too. Do you know what would form? If you oxidize zinc using oxygen, you'd form zinc oxide. Zinc oxide, people love it in sunscreen, you know. It gives you that white sunscreen. Some people like that a lot because it's good at blocking ultraviolet. These are the last kind of redox that are covered in this are combustion. You know, metals can burn. Some metals are hard to catch on fire. You know, iron is hard to catch on fire unless it's powdered iron or steel wool. If you have steel wool, then you get a nice little flame. And, I mentioned before in the like the Boy Scouts or the Scouts or whatever. You go on camping trips, and it used to be the way you'd start a fire is you get kindling, you know, you get little pieces, twigs, whatever, to start the fire, right? But then somebody told me, oh, you should use steel wool. And steel wool is an easy way to start fires. You don't need as much kindling, and kindling sometimes is hard to catch on fire, but steel wool is easy to catch on fire, and it burns pretty hot, and so it can catch wood on fire. It's expensive, though. So I don't know if you want to use steel wool. Kindling's free, you know. So I'd probably go with kindling rather than, and steel's getting more and more expensive. So, but those are hard to burn. There are things that are a lot easier to burn, and that is a lot of organic compounds like, or what are organic compounds? Organic compounds are carbon-based compounds, but this is considered inorganic. Carbon dioxide and carbonate, those are considered inorganic. And one of the reasons is in terms of redox properties, you know, carbon monoxide is considered inorganic, but organic compounds are usually contain hydrogen in there. Sometimes oxygen. We don't always have to have oxygen. And so if it's just carbon and hydrogen like methane, that's organic, CH4. Methane's an excellent fuel. Carbon dioxide doesn't burn, but methane does burn. And so let's take a quick look at methane versus carbon dioxide. Methane and carbon dioxide are on opposite ends of the spectrum. Methane is at max electron rich. Carbon dioxide is at max electron poor. And so, what do you think the charge on carbon and methane is? -4. And so that's max electron rich. It's -4 on carbon. And CO2 is +4 on carbon. To show that, I write that in parentheses here. -4 in parentheses above the carbon. Hydrogen's a +1. And over here, it's +4 and -2. So CO2 has no more electrons to give. Unless you take it from oxygen, but it's extremely hard to take it from oxygen. If you can take the electrons from oxygen, then you have something that can burn water. Because water could theoretically burn if you could take the electrons from oxygen. But how hard is it? Extremely hard. It's extremely hard to catch water on fire. But probably could do it in the sun. Plasma in the sun. But here, does this burn? No. Does this burn? Yes. And so as long as we have some electrons there to give up, then it burns. It'll be a reducer, what we call. And so we want to burn stuff. And the oxidizer that we're going to use is just oxygen. And so if we have a CHO compound and we burn it in oxygen, we're going to burn it to the max, which would be and water. Hydrogen's going to end up in the water. Also, the oxygen's going to end up in the water. And so, this is redox. This is combustion. Redox combustion. So these are redox combustion. What the driving force is going from stronger oxidizer to weaker. So this is our stronger oxidizer, SO. This is our stronger reducer, the organic. And this is going to be our weaker oxidizer, and this is going to be our weaker reducer here. And so we're just going from stronger reducer, stronger oxidizer, to weaker oxidizer, weaker reducer. That's we'll talk more about that later. This is the combustion of methane. We just got to balance this, basically. But when we combust organics, it forms CO2 and water. As long as it's CHO. If we have CHN, then it forms oxides of nitrogen. If we have a CHS, it will form oxides of sulfur. And so, as long as we have this, we're okay. All the ones we're going to deal with are oxides of carbon. So here, this is ethane. If we take ethane, it burns. Ethane burns to form CO2 and water. So when we balance this, we balance the oxygen last. So here we have 2 carbons. Here we have 1 carbon. So what are we going to do? 2 in front of this. Over here we have 6 hydrogens. Over here we have 2. So we'll put 3 in front of this. So we'll get a 2 and a 3. And that leaves the oxygen. And so over here I have 2 times 2 is 4, plus 3 is 7. So I have 7 oxygens on the right. I need 7 oxygens on the left. So you know what they do? 7 half. And that gives us 7 oxygens, and then it's balanced. But do you want the fraction there? Sometimes yes, sometimes no. If we want to get rid of the fraction, how do we do it? Multiply, double everything, so we can get rid of the fraction. Sometimes we leave the fraction in there because we want to know per mole of ethane, what do we get? This is combustion. And so the combustion reactions you're going to encounter are going to be CO2, forming CO2 and water. Then your book, your book does double replacement precipitation, double replacement neutralization. I don't like to subdivide it into so many different categories. I just like to look at the 3 driving forces. So this is just double replacement. It's I call AB plus CD. you know, but now they're coming up with different patterns. We don't want different patterns. We just want one pattern, you know, and not so many subcategories. And so the precipitation, we already did this. These are the solubility rules in your book. These are more detailed solubility rules, so this would probably be better, but this is too much to memorize. And then the solubility you can get from other sources too. But this is pretty good, but you know, that's 2 pages worth of tables we're not going to deal with. So here's a precipitation reaction. This is very similar to what we saw before. Here we're going to precipitate out lead-2 bromide. Sodium nitrate is aqueous. So if it's lead-2 bromide, we do not split it apart. Lead-2 bromide stays. It's an insoluble salt, so it stays. Whereas the other salts are all soluble. And so the net ionic is just going to be lead like bromide ions to precipitate out lead-2 bromide. Lead likes chloride, bromide, and iodide. Then they say double replacement molecule. Double replacement molecule is just weaker acid formation, you know, like water. And so your book is going to subcategorize the double replacements into these, but they're all kind of the same. So this is just an AB plus CD again. AB plus CD. Here we're going from a stronger acid, HCl, to weaker acid, water. Stronger to weaker acid. Strong acid, we ionize. Sodium hydroxide is a soluble salt. Yes, you might say that's a strong base, but all sodium salts are soluble, so we treat this as a soluble salt, sodium hydroxide, sodium ions and hydroxide. Water, leave alone. Sodium chloride, split apart. So the net ionic is just H plus acid and hydroxide base makes water. Here. But that's just double replacement there. Formation of unstable products. So when we have acid, H plus, and carbonate, they like each other, and they form carbonic acid, but we need to remember that carbonic acid is not stable. This is the number one. You have to know that carbonic acid has to be decomposed into CO2 and water, or water and CO2. It doesn't have to be order. This one's not as common. You know, hydrogen ions and sulfite make sulfurous acid. This one is encountered a lot less. And then this one's supposed to be ammonium ions and hydroxide ions make ammonium hydroxide. Ammonium hydroxide decomposes into ammonia and water. But for sure, the top one, this top one, you need to know here. That it, yeah, right. This is by far the most important one. These other ones are less frequently encountered. Here. This is the gas formers we talked about. There are more. So this is a reaction we did yesterday. Sodium carbonate and hydrochloric acid. Sodium chloride, CO2, and water. No, do you see carbonic acid there? They didn't write carbonic acid there. They just went ahead and decomposed it into H2O and CO2. And so we already did the ionic equation for this and the net ionic equation for this. It's tricky. HCl breaks up nice and clean. H2SO4 is a bit more of a mess. Double replacement with undissolved reactants. You know, this is too many subcategories. The undissolved reactant, okay, aluminum hydroxide is solid here, but it's still double replacement. And so you don't have to memorize all these little subcategories. Huh? Yeah, right. We already talked about aluminum hydroxide. Other double replacement reactions. I don't really care about other double replacement reactions. We're just looking for 3 driving forces. In this particular reaction, there is no driving force. There's no precipitate, sodium salt soluble, potassium salt soluble, nitrate salt soluble. There's no precipitate. There's no gas. There's no stronger to weaker acid. And so when we have there's no driving force, what happens is nothing changes. So you start off with this, you end up with this. And so what we say is NR. NR stands for no reaction. So if you have no driving, all you need is 1 driving force. But if you have 0 driving force, then what we're going to say is NR. And if we have an NR, it's good to say no PPT, no gas, no stronger SA to weaker WA acid. And if you get it wrong, you have to be careful. When you have an NR like this, what if you got it wrong? If you got it wrong, you lose a lot of points. So it's best to write everything out and then say NR. But what some people do is they just go ahead and say NR right at the beginning, but oops, they got it wrong because they didn't realize something.
NR for everything.
Yeah, you be careful. And then they have this map, you know, with all the reactions.
Okay.
That's too many. Do you see that?
It's an exam by itself.
Yeah, so I'm not even going to talk about this. I'm going to skip that. So what we're going to do is we'll just do like let's have a quiz. This is just going to be some practice of chapter 5 type stuff here. This chemical reaction stuff we're going to be doing on Monday and Tuesday next week too. But you could, the quiz rules are the same. You can work with those. Whatever you want. Somebody needs a eraser. All right, let me make this bigger. It might be hard to read. Can you see that all right? I might make that big. So the average mass of the water, the molecule, can you see the periodic table there? The hydrogen, you might have it memorized. What do you use for hydrogen, the average? 101? 1.01? And then what do you use for oxygen, the average? 16.00. So 101 and 16.00 are the average masses for hydrogen and oxygen, respectively.